Welcome. I'm Risto Miikkulainen. I'm going to be talking about how we can evaluate medical aesthetics treatments through evolved age estimation models. This is joint work between a number of people in the Cognizant AI labs in San Francisco, as well as other folks around the world working at different parts of Cognizant, and a collaboration with AbbVie in Irvine mostly, who are experts in the domain in medical aesthetics. They provided the data as well as some of the goals and evaluations. Okay, so let's start with the question of what medical aesthetics actually is. And you may be familiar with that, but it is generally a family of treatments intended to improve the patient's appearance. And it might be due to surgery or reconstruction or something, but a lot of it has to do with improving how the people electively look, feel about themselves. So it most often alters the facial skin texture through some kind of an injection like Botox or fillers. And like here in this image, the goal might be that you get rid of the wrinkles and therefore may appear younger. But that is a little difficult to evaluate and measure. It's very subjective whether somebody looks younger or somebody looks more natural or better. Now, if we actually make age reduction a primary goal, it becomes measurable because age is something that you can actually estimate. We know the actual biological age, and then we can measure the perceived age and see if there's improvement. But it's still subjective, and we would like to make it quantitative and objective using AI, and that's the goal of this work. So the starting point is a general neural network approach for estimating ages. And there's a number of those studies already based on DenseNet or EfficientNet, and most often a data set such as the celebrity data set on the right here, images of celebrities of different ages. Now, we have an idea of improving this in a couple of ways. First of all, utilizing an actual data set of patients, real people instead of celebrities, and also optimizing the network architecture through evolution. So we don't just take an off-the-shelf image processing network, but evolve its elements, its design to this task. And hopefully we get better age estimation that way. So that's the first goal. The second one is to use that hopefully improved ability to estimate ages to demonstrate that the treatment really works, that the perceived age is reduced as a result of the treatment. And to measure that, we use the neural network. In order to do that, we need to estimate our confidence on the age estimation. And for that, we use something called RIO, which is a Gaussian process model that models the errors in a point prediction. And therefore, we can put confidence bounds around. So that's the approach. So the starting point, like I said, often is in data set of celebrities, IMDb data set. And that kind of works at first, but it turns out that these images are difficult to estimate age from, because a lot of times the celebrity has a lot of makeup. They might have some medical aesthetics work done already. So the age is a lot noisier to estimate than from more natural images. Now we get something like 7.43 years error, medium absolute error in age estimation. So if the person is 40 years old, the network might estimate 47 or 43, something like that. So it is suggestive, but it's not quite accurate enough to decide whether some treatment is working. So that's a starting point, baseline. So in order to do better, we collected two patient data sets, our colleagues at AbbVie did. And they were of different sizes, roughly the same age range, pretty broad age range, 10,000 images, 20,000 images, but also different resolutions. So the first one was a little easier, a little less resolution. The second one was a little sharper and a bit more broader as well, larger data set. And using DenseNet again to train age estimation on it, actually reduced the age just right off the shelf quite a bit. So now we're talking about 3.5 years. So 43.5, maybe, or 30. 6.5. And that is already a significant improvement. We're getting to a ballpark where it's meaningful to ask and evaluate whether treatment is improving. So having a realistic data set really matters. And we have them now from our colleagues at AbbVie. So the next step is then to use this data sets to train neural networks, but not only that, but evolve their architecture, evolve their parameters in order to do better than the off-the-shelf DenseNet. So we used a platform called Leaf, which is developed at Cognizant, and is a neural architecture search method, as well as optimization of many other aspects of neural network design. In particular, we used 3 sets of optimizations. We optimized the learning parameters, optimization parameters like learning rate and so on, decay. Also data augmentation parameters, like how much we shift the image, whether we do a horizontal, vertical flip, and so on. It's kind of interesting that this is, I think, the first time we reported results on data augmentation evolution. And also then architecture hyperparameters, like what base model is used and what kind of blocking we use and so on. We also had an element for optimizing the training loss. We do have other work. Even in this conference, Santiago Gonzalez presents TaylorGlow for optimization of loss functions, but we didn't go quite that far. We used 2 different loss functions and optimized the linear combination of those over learning. But it makes the difference what your loss is that you use to learn from. So this was all these were all optimized through evolution as we were training the networks. And here are the results. This kind of complicated graph, but let's walk through it. So initially on D0, the first data set we had, there were data scientists that were trying to optimize the architecture starting from ResNet 50. That's the base. And they optimized the parameters of ResNet 50 by hand. And they actually got pretty good performance right here. That's the line for D0. We started about the same time with ResNet 50 and studied the evolutionary process to optimize those hyperparameters automatically. We pretty quickly got beyond the human design. And then we, at that point, shifted to DenseNet 169 and got further performance improvements. At that point, we got another data set, the D1, and humans eventually, for over several months, optimized the performance and got to quite good performance, something like 2.35 or something like that. We, of course, started at the same time, the evolution, and using the same network, DenseNet 169, off the shelf. We started a little bit weaker than we did with the previous D0 data set, because we optimized for that data set. But then through these optimizations over time, we improved quite a bit. Now, the humans used EfficientNet B6, so we also switched to that. We used the same hyperparameters that had been discovered for DenseNet 169 and switched to EfficientNet B6 and got further improvements, and eventually, again, exceeded the performance of the best human design network by a significant margin. So this is quite interesting. This tells you kind of the whole experiment over several months, how we can improve the performance of these networks, starting from those that are off the shelf and improving even over the best human designs. Data scientists who know what they're doing and spend several months optimizing the networks by evolution, using evolution to optimize hyperparameters and aspects of the experiments, we can do even better. And the main reason for that is that we can actually optimize with evolution many more parameters simultaneously. And there are interactions between them that we can take care of. And that's how we can go further than humans can. Okay, so, but we also discovered some interesting things. Some of them are more or less accidental, but demonstrate that there is power in evolution. First of all, the data augmentation was meaningful. The evolution discovered that vertical flips were useful, which is really funny because you don't expect the faces upside down to be helpful in training. But when we looked at the data, it turned out that the images were actually rotated 90 degrees. And a vertical flip actually makes sense. It flips the left side to the right side and so on. And evolution discovered that on its own. It made sense for it to discover it, even though we didn't know that it was a useful data augmentation operation to begin with. Another one was a width shift range. So now we are shifting towards the forehead or the chin, or reducing the range. And it turned out that this was useful because there was less overfitting to aspects that didn't matter that much, like forehead and chin. The treatments were in crow's feet and nasolabial fold and so on. So that's where the age estimation actually mostly is based on. We don't have treatments in this study yet. And also the losses were different at different stages. The mean absolute error was more useful in the beginning, and it caused less overfitting, more regularization. And then we shift, or the evolution shifted to cross entropy later on, and was fit the data better. So that was also an interesting discovery. Different losses work at different stages of learning. So now, armed with this kind of a network that's really good at estimating age, we can do something more. We can now start evaluating treatments. And we should also point out that this level of performance is actually quite good. We're looking at, again, if the person is 40, our estimate might be 4.2 or 38 or so. That's pretty accurate. And it turns out it's actually generally better than human estimation. It wasn't head-to-head comparison with human performance, but other studies have reported 3 to 4 years error. So they might estimate 34 or 36 to 44, and we have 38 to 42. So we actually quite a bit more accurate with this network that was designed by evolution. So now it's so accurate that we can start looking at whether the treatments really matter, whether they make a difference in estimated age. But we need the RIO first to estimate confidence, so we can claim that with confidence, that result. And RIO is a methodology, was developed by Xinxu and Elliot Meyerson at Cognizant. And this is a mechanism that can be added to any classifier, or actually in this case, it's a point prediction neural network. For instance, here, neural network performs at a certain level, it makes certain errors, there are residuals. It's not exactly accurate in producing the value like age. So it's a residual value. And we fed a GP model, Gaussian process, to those residuals using an input-output kernel. So it's sensitive to both input and output regularities. And it turns out the genetic process, of course, gives you confidence intervals, the stochastic model of where the errors are. But also because there is such a distribution, we can find its mean and shift the outputs in that direction. So we can correct errors. We can come up with more accurate outputs when we add this Gaussian process model on top of the neural network. So it estimates uncertainty and also improves the predictions. It's kind of surprising why that would work, because we already trained the network to be as good as possible, or we could train a GP alone in this data. But it turns out that they capture a little bit different aspects of the problem, that the neural network is very expressive. It has high variance, and therefore it learns structure that the GP might treat as noise. And whatever is left is actually easier to learn, and the GP can capture it, and it can do it with more regularization. And therefore, we do get combination of two different facilities, and the sum is more than its parts. Okay, so now, in order to evaluate the treatment, we needed a treatment data set. Previous data sets only had phases without treatment. So here we have a single Botox study with about 787 patients, again with the same kind of age range, thousands of images taken before treatment, and then a lot of more images at different intervals into the future after treatment. First week, second week, and then every month until 6 months. There were 2 different treatments in the dataset with different volumes, the same Botox toxin, but more or less. And we also had a placebo set of patients, those who did not get Botox but got a saline liquid instead, injection instead. And we also removed the pre-treatment age bias. So we estimated the age at the treatment, before treatment, and if there was a significant difference, it was reduced or reducted. And therefore, we get less biased estimates of the age effect of the treatment. And before we started, we also evaluated RIO with the pre-treatment data, again, just age estimation. And it turns out that it was able to improve the accuracy of the age estimation a little bit. And this was more uniform set, so we got pretty good accuracy in age estimation to begin with. and RIO added to it, and that's a good starting point for evaluating the effective treatment. We also notice that the coverage is pretty accurate. So when we have a 95% confidence interval, indeed 94.2% of the samples fit in that range. So and same for 90 and 68. So RIO has a pretty good, strong performance in both improving the performance as well as estimating the confidence. So here's the bottom line. Simple graph that makes a very big point, that here's the placebo effect. The treatment was done here, and here's week 1, 2, 1 month, 2, 3, 4, 5, 6 months. And here are the 2 treatments, and these are standard error bars. So we can see that the treatment results in significantly lower age. This is the difference from the actual age. And the perceived age after 6 months is about half a year younger. And of course, the person is half a year older, so it's a reduction of 1 year. And this is just a single treatment. It's like the basic experiment that indeed a single injection already reduces your age by about a year. And then in a typical treatment, there will be further injections, the second one, and maybe more, and you can reduce the age even further. So this actually shows you that there's a very fast reduction in about a month or 2, and then it's stable for at least 6 months. And that's typically where the second injection comes in. And that's actually a really good result. It demonstrates that there's a foundation for it that can be quantified. In the future, we can evaluate the treatments that are more extensive, multiple injections, maybe also other types of treatments or combination of treatments. So now with this model, we can evaluate how well they are working objectively, and therefore make progress and come up with better treatments. We could potentially extend the same kind of mechanism to other outcomes, for instance, natural look, like using perhaps GANs, and there we needed some kind of objective measure to estimate that. Age was easy because it's actually numerical. There's a biological age that can argue with, but it will be a little harder for other dimensions, but it might in principle be possible. And also then extending further, not just looking at the age, but also predicting what the effect might be of a particular treatment. And then when we can do that, possibly also optimize what treatments to do in order to achieve certain goals. Okay, so to conclude, the architectures of deep learning that do age estimation can be optimized to the task using evolution of many parameters and aspects of the experiment, including data augmentation. And if we do it, we can do it better than humans can. And also the age estimation networks work better than humans. The accuracy of the estimate was better than typical human accuracy in this task. And overall, and of course, yeah, we demonstrated that treatment is effective, the perceived age is reduced. But most interestingly, this is a new role for AI. It takes a problem that's difficult to quantify, like does the treatment work? And it is subjective. It does subjectively, people think that it does, but can we make it quantitative? And here we use AI in that role, make a subjective evaluation quantitative. And we believe that there might be more applications like this in medical field and others where AI can play this role. Okay, thank you.